All right. Hey, everyone. Welcome to the special session of Jeff's DSUA-111 Data Science for Everyone special session where I'm going to talk about how to do regression, specifically how to find an R-squared, well, how to do the regression and then find an R-squared value for it, find a confidence interval for it, find a p-value for it, and make a residual plot. That's like the important thing here. I ended up just making a full project notebook where I just went through the questions of the project with a sample data set. But yeah, I'm gonna kind of be rushing through the stuff before the regression so that we can get to that. And actually, even though it wasn't in the email that I sent last night, I made a separate version of the regression notebook that uses scikit-learn, a library called scikit-learn, to do regression instead of stats models. Yeah, stats models, which was the name of the package that I used for regression in the notebook I sent out last night. So yeah, let me share my screen. And basically, I'm just gonna start from scratch. So we go to GitHub. And for your sake, it's in the email, but you can go to github.com/j_powerj/DSUA-111-sections, right? And you'll see this, and GitHub does not, kind of on purpose, does not make it easy to download files directly. So, but I'll just show you how to do it. So first I made this regression_blank notebook that literally it's just all the questions from the project with little blank cells where you can fill in your work, right? So if you want to download that, the least painful way to do it is you open it, right, in GitHub, but you don't save this file, right? This is like a kind of a formatted HTML file. You click raw, and then you right click on what comes up, which is like the code that's underneath a Python notebook. Then I'll just put it on desktop. So regression blank, right? And so it's on my desktop, which means that now I can go to dsua-111.rcnyu.org. I can spawn my server and wait. Don't know how long this will take. And cool. Hugo's now awake, so you might get a cat in a minute. But yeah, now that I am in here, I can click upload, right? And I'm on my desktop, so I can click regression blank.ipynb, right? And then it's a little weird because it doesn't immediately upload it. It's kind of weird. You click upload and then you pick the file, but then you have to actually click the upload button again. But once you do that, you'll see it, right? I have regression blank here, right? And that is, so I've just transferred the Python notebook from that GitHub repository to my server, right? Cool. And so you can just go through and fill these out, right? So you replace describe briefly the question you'd like to answer with your answer, with your response. But that's not what I want to do. Whoops. Right now, what I want to do is go back to GitHub. Sorry. Okay, go back here, go back to the full repo that lists all the files, and instead we'll start with regression.ipynb, even though, like I said, I just 9 minutes ago, right, uploaded one that uses scikit-learn, but we'll start with the one that uses stats models. And like I said, I'm going to be going really fast. I'm going to try to go really fast through everything up to the regression so we can just talk about that and show you how to do it real quick. So yeah, this has a fully filled out project. And again, to download it, I click raw, I right click save page as, I'll call it regression.ipynb, go back to my Jupyter Hub, upload, regression. Now it's regression instead of regression blank. Upload it. And now I can open that. All right, so one very important thing is that I had a bad feeling, and it came true that since we just uploaded it, but we didn't specify a kernel to use yet, the default Python 3 kernel is what it's going to open with. But you don't want to use that kernel for this class, right? Because we're using all these additional packages like pandas, NumPy, matplotlib, and stats models. So make sure you do this, right? You click kernel in the menu bar and then change kernel, and then pick the DSUA-111 environment. Cool. So yeah, this is my sample project. The pre-step is, what question would you like to answer? I just said, like, I worked as an economist, and it basically, like, every study of in development economics is about, like, oh, let's look at like a present day property of a country and use it to explain a present day, another present day property. Whereas, like, to me, my like angle on it is that I'm interested in, the role of like the history of a country in determining things about its economy or its society. So yeah, I just talk about like the question or topic I'd like to explore is like, have like a variable about like the history of a nation, and then a variable about a modern day thing that economists care about, and look at the linkage between the two. So yeah, in this case, specifically, then question 2 says, find a data set that may help to explore the questions. First, describe where you found the data set. So I found a data set on colonial history. There was actually one here that selected on the dependent variable, right? It only included countries that were colonies, right? So we couldn't, and it didn't include countries that were not colonies, which is frustrating, right? Because that's what we learn in class, that you can't derive any knowledge about, oh, what's the effect of colonization on a country if we don't ever observe non-colonized countries, right? So that's selection on the dependent variable. Whereas this data set with a link that looks very similar but is different has like all the countries, right? And so including colonized countries and colonizer countries. And then present day socioeconomic conditions, like there's a bunch that I could have picked, but I picked one on life expectancy by country, which was nice because it let me, even though it's like it's called a panel data set, which means that it has every country and every year. We haven't learned how to deal with like that double layer of complexity in this class. We've only learned how to deal with what's called cross-sectional data. So what I did is like the interface of the WHO let me just select the year 2016 and then download a new type of data set, right, where it's just the life expectancies in 2016, which is the latest year that they have data for. So instead of like country year being a row, now I don't have to worry about the year because it's always 2016. So I just get the country. All right, so I downloaded that. I'm gonna have to upload that. So yeah, let me show you that. So basically I have these two CSV files, right? One of the colonial history and another with the life expectancy data, and use the same upload function, but instead pick your CSV files, right? So first I'm going to pick, it's in here, here, here. The data set on colonial history is this call data 110.csv. So I click upload on that, and then click upload again, and this time I have lifeexp.csv. Was the name of the life expectancy data set. Cool. So now, right, those are in my root folder of my Jupyter Hub now, so that I can use them. All right. So now back to the notebook. Yeah, specific variables that I want to look at are end date, which is the date of independence of the country, whether it's like, the US and it's 1783. They declared independence in 1776, but they didn't get it until 1783, right? So, or like South Sudan, which received independence in terms of like UN and international recognition in 2011. So that's the latest country. And then life expectancy at birth in years is the variable that I want from the WHO data set. Cool, and the unit of observation in both cases is a country, right? Whereas until I filtered the WHO data, the unit of observation would have been country and a year, but now it's just a country. So yeah, if you could change this data set in one way to make it better for analysis, what would that change be and how could it improve your analysis? There's a million things you can think of for this, but one massively important variable is which country was the colonizer, right? Because different colonizing countries like the UK or France or Spain, Portugal, they all had different like ways of running their colonies, right? And so you can imagine that different methods for running the colonies would result in different public health outcomes, right? So like colonial powers that invested a lot in like public health infrastructure, you know, training doctors and building hospitals and stuff like that, probably have higher, the countries that like were, you know, under that system, we would expect them to have higher life expectancies than other countries under other systems that do not invest a lot in public health, even if they have been independent the same amount of time, right? So that's a huge variable that's missing. I talked about here, there's this, you know, pretty well-known book, Leopold's Ghost by Adam Hochschild, that talks about how like Belgium, you know, no offense to if there's any Belgian viewers, but yeah, they were one of the harshest colonial regimes in terms of like negative effects on public health. So we'd expect that, you know, a Belgian colony that was independent for 70 years versus like a non-Belgian colony that was independent for 70 years, the non-Belgian colony, we'd still expect to have like better life expectancy outcomes, even though, right, everything else is like the same in that hypothetical example. So yeah, that's one thing I would improve. That's how you can answer that. Import the data set into Jupyter, show the first 5 observations, and if you had to do any work to get it into an uploadable format, please describe it. So I had to do a thing where the first thing I did was like, I just deleted anything in one of those data sets that wasn't in the other and vice versa. And then I also had to change the names of the countries so that they matched up. So for example, sometimes it's the Bolivarian Republic of Venezuela, whereas the colonial, so that's how it was listed in the life expectancy data set, whereas the colonialism data set just said Venezuela. So I have to update those. I actually wrote a bunch of code to do it like through, you know, pandas and NumPy, but it looked really gross and I didn't want to scare people, but I can show that to you if you want. But the easier thing to do for the sake of this class is just, you know, you can go in and manually edit the CSV, for example, in Excel, or like I use OpenOffice Calc, which is an open source like free version of Excel. So anyway, we do all our imports here. You know these from class. I import lifeexp.csv. Well, I have to run it. Cool. And then we do read CSV on lifeexp. That's the CSV that I just uploaded. And we call .head, right? And that gives us the first 5 rows. Now, even though I did the cleaning that like the little bit of cleaning that I mentioned of like making sure the rows match up and the country names match up, I still had to do a bunch of cleaning to get rid of things like, okay, get rid of the variables that I don't care about for this analysis. And also like you'll see in this one, like there's actually 2 header rows. See like the first header row here is like a full sentence explanation of what the variable means. And then the second row says like, is it for both sexes or male or female? So I only care about life expectancy at birth for both sexes. So the point is like, I just wrote a little bit of code here to throw away this first row that's just labels, and also to throw away all the variables that we don't care about, right? So that's this one that says, just keep iloc means like integer location, meaning like the number of the row and the number of the column versus the name of the row and the name of the column, which would be loc. But iloc says, give me rows from 1 onwards, right? And remember, computers start counting from 0. So from 1 onwards, it means Afghanistan row and onwards. And then I just want columns 0, 1, and 2, right? Remember that this notation here means from the first number to the second number, but the second number is exclusive. So it will get 0, 1, 2, and then it will not get 3, even though that's the end of the interval. So we'll get row 0 here, which is the country. Column 0 here, which is the country name, column 1, which is the year, column 2, which is life expectancy at birth, and then that's it, right? So then once I run this, I have a data frame with only 3 columns, so it's easy for me to rename the variables from this like long string and like unnamed, which doesn't help us, into just country, year, and life exp. And I do that by just saying, yeah, you get it. Columns, data frame.columns equals this list of names. And finally, this is a little weird, but it didn't parse these as numbers, and that's because like this value right here was always a string instead of a number, so it couldn't parse like the full column as numbers. It said, oh, both sexes, I don't know how to convert that string into a number, so it just didn't. It left them all as strings. So now that I've gotten rid of the row that has the strings in it, now we can safely parse the whole column as numbers. So for that we use pd.numeric, and we just plug in the column that we want to convert. Cool. So now it looks like this. Well, yeah, run this. And then it looks like that. And so yeah, just 3 columns, right? Country, year, life expectancy. Then for the colonial independence data set, similar thing where it looks really gross when you first load it. So I just want to keep columns 1, which is the country name, and 4, which is the date of their independence, right? So I do that, and then I rename them to be country ind date. And then this, you don't really have to worry about it because hopefully you'll have a variable in your data set already. That's what you want to study, but in my case, I had to transform it, right? Because I had to take the first 4 characters of this independence date. That gives me the year, right? And then I wanted to take 2016 minus that year to see in 2016, how many years had that country had since independence, right? So like for Afghanistan, 1919 and then 2016, right? So meaning we're looking at data from 2016. So 1919 to 2016, that's 97 years of independence, right? So this line just computes that. And if you want to know, like, it just says, okay, take the end date column and apply this like logic to it. It's called a lambda function in Python, but all it says is like, for everything you give me, X, take 2016 and subtract this thing here, where I'm taking the first 4 characters in X, right? So this, we've seen that says X, and give me the first 4 characters, 0, 1, 2, and 3, and then convert it into an int, and then take 2016 minus that int, and just give that, right, as the result. So this is just a shorthand way to make like quick calculations on each element in a column. So I'm saying year since end equals year since independence is the independence date with this transformation applied to it. Cool. And so I get these nice numbers where, yeah, Afghanistan, 97 years since independence, Albania, 103 years, and so on. I computed it by taking this 2016 minus that. Cool. Now merge, again, you don't have to know this because you can just have like a single data set, but I figured this would be helpful for people if you have, you know, one data set on one variable and another data set on another variable, and you want to put them together. You just use the merge function, right? And so what happens is you say, okay, I'm going to take my call df, that's this data frame right here, and I'm going to merge it with life df. So that's the life expectancy data frame that I have up here. And you just have to tell it like what variable it should merge on, right? In this case, it's on country, right? And then it will work because this data frame has a country column, and this data frame also has a country column, right? And so it'll just pair those up and make it like combine the 2 data frames together by saying like, okay, Afghanistan row from this data frame and the Afghanistan row from this data frame, just combine them, right? So now it has all the columns of both data frames. Cool. How equals left, that just means like if there's it's kind of a long story, but it just means that if there is a row in the data on the right, which is the life expectancy data set, and it's not in the left data set, which is call df, you can tell it just because the order, right? Call df is on the left here, whereas life df is on the right. So how equals left just says, I just only want to do the merge for the countries on the left in the left data set. Like if there's a country in the right data set, in the life expectancy data set, that's not in CalDIA, just don't use it. Don't merge it, right? And so lastly, indicator true is super helpful because when you run a merge, you're like not sure like, okay, well, did it work? Like, did it successfully like pair up the countries in each? And if you do indicator equals true, then you can look at this. It creates a column called underscore merge, and it will, so here, I'll show you the full thing. Merged df underscore merge, right? It'll say both if it's successfully like, oh, I found that country in both, right? But it'll also say left only, left underscore only if it only found it in the left, and right underscore only if it only found it in the right. But in our case, so I'm checking like, oh, I want to see anything that didn't, any country where it didn't find that country in both data sets. And we know it's successful because there's nothing, right? It comes up with an empty data frame. So great. And now we can just drop that variable because it was just to tell us whether or not our merge was successful, right? So I drop columns merge in place. And then we look at the first 5 rows just to see that we have a final a final combined data set that we can use, right? Because we have our independent variable, years since independence, and our dependent variable, life expectancy. Cool. And then it says conduct 2 different manipulations. I used shape just to see like, okay, how many rows and how many columns are there? And then I just said like, okay, so I've learned that there's 183 countries and 5 pieces of information for each country, right? Number of rows, number of columns. So that's one manipulation. Manipulation is a weird word because it makes it seem like you're changing it, whereas really like shape or value counts, it's just showing you information about it. It's not really manipulating it. But anyway, the second time I just was like, okay, well, I would just want to see kind of the range of my data set. And so I just wanted to sort by years of independence. So I just wanted to see like what are the countries with the lowest values and what are the countries with the highest values. So sorting and then displaying the data frame will tell me that. So yeah, I sort by years since independence. And yeah, I get South Sudan only had 5 years of independence in 2016. Montenegro, East Timor, South Africa, post-apartheid, Eritrea, independence from Ethiopia, right? Whereas like the highest values are for old like European countries, right? Austria, Portugal, UK, Denmark, and France. So like according to this, yeah, we can look at the end date and like France is like founded in 940 or gained independence in 943. It's a little weird to talk about like independence in medieval times because like colonization, like people didn't really think of things in terms of colonies back then so much. But anyway, the point is like the person who made this data set said, oh, these are the founding years for these countries when they were independent from any other power. So we're going with that. And, you know, in the discussion questions, you can talk about how dubious that is, which I try to do. Okay, now 2 different types of graphs, question 6. We've seen that. I just made a scatter plot, right, where X is my independent variable, years since independence, and Y is my life expectancy. So what I learned from this plot is that, look, there's like these outliers here that have extremely high values, and it's making it hard to see the general relationship, right? Because the plot has to be like wide enough to fit this, like France and Denmark, which have over 1,000 years. So it's hard to see like the relationship among most countries, which are between like 0 and 200 years old, right? And so we could just like arbitrarily drop it, but then here I talk about how like 1648 is an important date in international relations because that is the date when the Treaty of Westphalia was signed, which is essentially like when all the European countries, and not just European actually, like a bunch of countries in the world like got together and decided that, oh, we're gonna like establish this thing, territorial sovereignty, which means like, okay, each land has like a government and like we recognize that the people in that land have like answer to that government. The point is like, it's just in like international relations theory, it is a reasonable year in which to start talking about like independence of a country from foreign control of their sovereignty, right? Because that's when like sovereignty came into existence as like, oh, there's countries and they have sovereignty over their territory. Anyway, so I just, talk about that, and I do what we've done in class where I say, okay, I want to make a new data set, merge DF TW, where TW is Treaty of Westphalia, where I just say, take the full merge DF, but then only give me elements where years since ind is less than 368, right? Which is 2016 minus 1648. And so I cut that, and it becomes a lot easier to see the relationship, right? Because these outliers up here are gone. So now we can start to see like there's probably like some sort of positive relationship, right? Like most of the countries with low life expectancy are pretty young, whereas most of the countries with high life expectancy have had like over 100 years of independence, right? Which is part of like the question that I wanted to answer. Is like that's a factor that should be taken into account when talking about life expectancy outcomes rather than just like GDP or something, right? Anyway, another plot is a box plot, right? Which Chris went over in class, but it's just, it shows you for a single variable, like it shows you the range of the variables, and then it shows you cut points for the median, right? So the median life expectancy is something like 73, whereas like the lowest value is like 50 and the highest value is like 85. Yeah, we can see the interquartile range and stuff like that. But yeah, you know that from class. Hypothesis formulation, yeah, that's just like taking what I've been doing so far and formalizing it as like independent variable. The thing that I think is the cause in my theory is amount of time since independence, whereas the dependent variable is life expectancy, right? Because I think that number of years since independence is something that affects life expectancy, right? So like input and output kind of cool. That's all from class. Hopefully you get that. Calculate the correlation coefficient. So Pandas has a function .corr, .corr. And the way you can use it is you can say, okay, take my data frame and I want to pick out the two variables that I want the correlation from, right? So you do data frame and then square brackets, and then inside the square brackets, whereas sometimes we've been putting the name of a variable, here we put a list of two variables, right? The two variables we want to find the correlation of, and then we call .corr on the result of that, right? So there we get a correlation matrix, which is, oh yeah, I gotta run this. Cool, so we get this correlation matrix, right? Which is kind of annoying because it's like, yes, a variable has a 100% correlation with itself. Like if you know the variable, you can perfectly predict the variable. Whereas it's these entries here that are not on the diagonal of the matrix that we care about, right? Because this is saying, if I know the years since independence, how well can I predict life expectancy? And vice versa, if I have life expectancy, how well can I predict years since independence? The answer is this number right here, which will scoop out using LOC on the correlation matrix. So we say .loc and we give it the name of the row we want, which is years since ind, and the name of the column we want, life exp, and so it gives us this value, right, 0.3323. And the way to interpret that is saying that there's a 33.23% correlation between years since independence and life expectancy. So it's kind of like, if we know life expectancy with 33.23% accuracy, we also we can predict years since independence, right? So that's one way to interpret the correlation coefficient. Now, write out your regression model as an equation. Yeah, this you'll learn, but in a regression model, you just have the dependent variable here, right, life x, and it's equal to, a regression has like two parts, right? It has the intercept, which is just like where the line, right? Because regression is like we're trying to find a line that can go onto this scatter plot here and like best be like a line that shows the relationship between it, right? Like, how do I draw a line on the scatter plot that does the best at like predicting the values, right? Summarizing it in a sense. And you can think of it just like, okay, so for 250 years of independence, right? We have these two countries that are 250 years old. So like a very good line at predicting these would go right in between them, right? Because it wouldn't, like if you put the line like up here on this point, it would perfectly predict this, but then it would do really bad at predicting this point. And vice versa, if the line went through this point, it would do a very bad job of predicting this. Whereas if you put it right through the middle, it does a okay job at predicting both of them, right? And so the point is you want to do that for like every point. You want to find a single line that you can draw that like best does the least bad at like fitting the points, right? So the point is it'll have an intercept, right? In this case, it'll be where that line starts, right? So at zero years since independence, where do we start life expectancy wise? And then, you know, ostensibly, then there'll be a slope, right? So that's beta. So beta 0 is the value of the intercept, the y-intercept, whereas beta 1 is the slope of our line, right? Which just says like for an increase in the x, which is years since independence, how much does our y, which is life exp, increase, right? So it's just like in pre-calc, where any line has an intercept and a slope-intercept form, right? Here's our slope, here's our intercept, and that's what we're trying to estimate, right? Beta, these are just variables that we're trying to use regression to estimate. Meaning, if we draw the best line, what are the values of these variables that produce the best line? Cool. And now that we have that, we can write out our null and alternative hypotheses like formally, because the null hypothesis for regression is just always that there's no effect of the independent variable on the dependent variable, right? That beta 1 is 0. That actually like the line is flat. There's no positive or negative relationship between the year since independence and life expectancy. Whereas the alternative hypothesis for regression is always that the values are non-zero, meaning there is an effect of the independent variable on the dependent variable. So an additional year of independence for a country does have an effect on the life expectancy. All right, now the regression. So the way that you do this is, I'll go over to the scikit-learn version because in lecture next week or the week after, Chris hasn't decided yet whether he's going to use stats models, the stats models package in Python or scikit-learn. So I'm just doing both here so that you'll be covered in either case. But so I started using stats models because I think it's easier. Basically, all you have to do is this one line, import statsmodels.formula.api as SM, right? Just like we've been calling pandas PD, we've been calling numpy NP, we call this like stats models formula API just SM for stats models, right? And then the only function we need to use is sm.ols, which means ordinary least squares. That's the type of that's the most basic type of regression, right? It's called ordinary least squares because it's trying to find the line with the lowest squared distance between the line and the points. So anyway, OLS for ordinary least squares. And so all we need to do is we say the result of our regression, right, equals sm.ols. We have to give it two things. First, we give it a formula, right? So just like up here, we had life exp equals blah, blah, blah times year since int. Here we say life exp, and then this tilde means like we're regressing on, right? We're estimating the equation between these two things, right? So we're estimating the effect of year since int on life exp. That's what this equation means. So you just put the name of the column containing your dependent variable and then a tilde, and then the name of your column, the name of the column in your data set representing the independent variable, right? So see, life exp tilde year since int is very similar to life exp equals blah, blah, blah year since int. The tilde is short for the blah, blah, blah part. And then you just have to tell it data equals like what data set it should pull these columns from, right? So that will like create the OLS model. And then there's just one more step, which is you call .fit on that. It's kind of weird because like what this code does up until the .fit is it creates a least squares model, whereas it creates a least squares model in stats models like format, but then .fit actually like does the estimation, right? It actually tries to find the beta 0 and beta 1 values, right? So like this kind of sets it up, and then .fit says now find the statistics, right? And so you can take that result variable and just call dot summary on it, right? And it gives you everything you need for these 4 questions on the project. I'll go through it, but you'll notice like you see R squared right here. We have a coefficient of years since end right here. We have the test statistic T here. We have a p-value here, and we have a, these 2 columns give the bounds of the 95% confidence interval, right? So in this case, well, I'll go through it. So yeah, interpret the coefficient. So the coefficient we can either get by just reading that, or where is it? Oh yeah. So we can call dot params, right? So result TW is this, the result of calling dot fit, right? So it's the thing we call dot summary on, but we can also say dot params, right? If we do result TW dot params, because I didn't run it. Okay. So result TW dot params, it just says like the intercept is this and the coefficient on years since end is this. And we only care about the second one. So here I'm saying beta 1, right? So our little slope variable here equals result underscore TW dot params, and then I tell it which parameter I want. I want this parameter right here. And then, you know, I just have a print statement that says a 1-year increase in independent variable, in my case it's years since independence, is associated with an increase in life expectancy of insert beta 1 here, years, right? So this is the coefficient. And so that's the interpretation. It's just a 1-year increase in my independent variable is associated statistically with an increase in life expectancy of the coefficient value years. So in this case, if we were just estimating a linear relationship, right, then the best fit line on that scatter plot that we did above is one with a slope of 0.038, which means for an additional year of independence, life expectancy increases by 0.03 years, right? So in other words, like a better way to interpret that in particular, because that's kind of a 0.038 years is hard to think about. That means that like after 25 years of independence, right? So after this 1-year increase has happened 25 times, each time the life expectancy goes up by 0.038. So after 25 times, you'll get an additional year, right? So the model predicts that for every 25 years that a country is independent, that country will have 1 more year of life expectancy, right? So that's like our finding, right? That's our finding of our regression. Now we can look at this column that's called like probability greater than t, the test statistic, right? That's our p-value. In this case, it looks like it's 0 because it's just so small that out to 3 decimal places, it is indistinguishable from 0. But you can get the actual value by doing, you know, result TW dot p values, right? So whereas before we did result TW dot params, now we can see that result underscore TW dot p values will give us, you know, the intercept has a p-value, and then also years since end has a p-value, and we're interested in the p-value for our independent variable years since end. So we say result TW dot p values, tell it we want years since end. And we have this, and it's still kind of annoying because it's in scientific notation. It's hard for me to interpret, at least. So we use this Python trick to just print it out in non-scientific notation, which is 0.000011, right? And so we interpret that the same way you've learned to interpret p-values through like lab and lecture, right? Which is that the test statistic value we got, which here is 4.539, this value right here. The probability that if the null was true and there actually wasn't an effect of the independent variable on the dependent variable, the probability that like we'd get that by chance, you know, even though there's no effect in reality, is extremely low. It's 0.0011% chance, right? So that's an extremely low p-value, which is why like it's considered like statistically significant, right? Next in the question, they want you to look at the confidence interval. So we get that here. It's a 95% confidence interval, which you can tell because the lower cut point is 0.025, which means 2.5%, right, of the data is below this. And then this high upper bound is 0.975, which means 2.5% of the data is above this value, right? So 0.022 and 0.056. So that you interpret the way you interpret confidence intervals, right? That if we did this sampling procedure over and over again, we would expect that the sample, like the beta that we get will be between 0.022 and 0.056, 95% of the time. Cool. And finally, yeah, the R squared. That is actually like right at the top. It's right here, right? So it's 0.110. Oh, I see. I should change this. Sorry, that means there's a typo. So it's 0.110, right? And that changes this because it's actually 11%, right? So it says, even though there's a lot of controversy, basically the way you can interpret the R squared is something like 11% of the variation in life expectancy is explained by the number of years since independence. So I talk about it here, but it kind of makes sense because this is like a huge macroeconomic variable that's the result of like millions and millions of different things, right? Like birthing practices, availability of healthcare, right? Like what type of healthcare system they have, like whether like how much exercise people get on average, the climate, and a million factors go into the life expectancy, right? So we'd be like very surprised if a single variable, like years since independence, would explain like a bunch of the variation in that variable, right? But so yeah, it's hard to kind of summarize it without like going into all these details, but long story short, we interpret that R squared value as saying that like 11% of the variation in life expectancy is explained by years since independence, which means that there's a remaining like 89% of the variation, right? Which we would need to explore using other variables, right? Like the one I mentioned at the beginning, like what percent of the variation would be due to which country was the colonizer, right? Due to whether you were colonized by Belgium or the UK, for example. And just as a last thing, there's this plotting library called Seaborn. So let me check that we have it. Yes, okay, great. The DSUA-111 Python environment or Jupyter environment has it. So we just import Seaborn as SNS, same as when we imported Pandas, same as when we imported NumPy. And it has this thing called regplot, right? sns.regplot, where you just give it the X column, right? The name of the X column, the name of the Y column, and then the data frame. And what it does is it shows the scatter plot like we did above, but it also shows what your regression line looks like, right? So in this case, we see this is what a regression looks like, where the intercept is 67.83, and the slope is 0.0387. That looks like this line. Cool. And we see like, does a pretty good job of splitting. So the example I gave before, like it doesn't do a good job of predicting these. It over predicts the life expectancy for a country with 250 years of independence, but that has to be balanced, right? With like it over predicts the life expectancy for countries with 250 years of independence, but it like under predicts the life expectancy for this country with like 275 years of independence, right? So it has to balance over predicting and under predicting to come up with the best like single line. So because of the extremely low p-value, we fail to reject, we reject the null hypothesis, right? If our p-value cutoff is 0.05, well, like 0.00011 is well below 0.05, and so we reject the null hypothesis, right? Which was that an additional year of independence has no effect, and we have some bit of evidence for the alternative hypothesis that an additional year of independence does affect life expectancy. Cool. And now the residual plot, this is like the last thing that I'm going to go through, because you can look at my conclusions. Like it's just social science stuff. I recommend reading it, but I don't feel like I have time. I want to keep this short. So question 14, though, asks you to make a residual plot. And what that means is actually the exact same as this plot here, right? It's the exact same as a scatter plot, but instead of where the x coordinate is the x axis is the same. It's your independent variable, right? Years since independence in this case. But the y-axis, instead of being your dependent variable, now on the y-axis you plot actually how badly your regression did for the point, right? Meaning like, right? So these dots are for these two dots here, right? The line overpredicted their life expectancy, right? Which means it has a negative residual, because the residual is just the y value of the actual point, right? The life expectancy value of the actual country minus the life expectancy value that the regression line would predict for that country given its years since independence, right? So this is probably like -2, you know, because it's like 74, whereas it predicted, the line would predict like 76 years life expectancy. Here it's like the actual life expectancy for the country is 70, but the line would predict 76, so the residual is -6, and so on. And so the nice thing is that stats models, when you run the regression in the results object, result TW, there's a value just called resid, right? And that is actually just an array that looks the same, right? It's the same size as your y value, in this case, our column of life expectancies, but now it's the residual value, right? So if we did, I'll show you what that looks like, result tw.resid, right? We see like, okay, the first country, the line overpredicted by 8.88 years, whereas the second country, the line underpredicted by 4.58 years, and so on. So that's what these numbers mean. And when you plot them, you get something like this, right? Where it's like centered at 0, because 0 means it perfectly predicted that country's life expectancy. And some, right, some it overpredicts by like up to 10 years, some it underpredicts by 10 years. But yeah, on average, it's balancing between overpredicting and underpredicting, right? So it's just this line up here, like tilted back down, right? So you imagine drawing a line from each point down to the regression line. That's now the height of that point on this graph. And it asks you to check for something called heteroscedasticity, which you can Google or you'll learn about, but that's just a fancy word meaning like, is the error in our regression correlated with our independent variable years since end? And what we see is like, when we run the regression, right? So this is now called a residual regression because it's a regression of the residual values on our independent variable. We see like there's actually we don't really see a pattern, right? Like it doesn't start like systematically over predicting or under predicting as years since end changes, right? It's like constantly striking a good balance between over predicting and under predicting. Heteroscedasticity is when, like, if we saw like, oh, the residual points, if they were like going up, right? Meaning if it was like -15 down towards 0 always, but then +10 up at like 300 always, that would be bad, because that means our regression is making like systematic errors based on different values of the independent variable. And it turns out data where that happens, it's kind of like that data violates the mathematical assumptions of the regression model, which means the regression is not the right way to study that data set. Which is, you know, sad if you do a research project and you run a regression and you find like, oh, actually there's heteroscedasticity. My residual plot has like a pattern of where like the residuals are changing systematically with the years since independence. But in this case, it's a flat line. We don't see any like pattern where like, oh, as years of independence increases, our predictions are systematically too high or too low, right? The errors are kind of uniform across values of our independent variable. Cool. You can read conclusions. Real quick, I'm going to go all the way back to GitHub and back to now I'm going to get regression_sklearn because I want to show you real quick how to do the same regression using the scikit-learn library instead of the stats models library. So I just click raw, save page as regression_sklearn. Now I go to my Jupyter Hub, click upload, regression_sklearn. Cool. So now we've been going through just regression .ipynb, but I'm going to open regression underscore sklearn. It's literally the exact same, except I changed the answers to the regression question. Right, so I'm just going to scroll down to that part. And yeah, here I replaced the cell so that now we're importing NumPy as NP, but we are also importing this. So from sklearn, which stands for scikit-learn, it's just it's a machine learning package in Python. So sklearn.linear model, right? Because regression is a linear model, it's trying to find the best fit line. Import linear regression. Cool. And now it's kind of annoying because you have to do this weird transformation on the data for scikit-learn to like it. So I'll just say what you do is like here, I took my column, right, usince int, and I transformed it from a pandas column into a NumPy array, right? Because remember, NumPy is the library that's like most nice for mathematical manipulation. And then scikit-learn requires you to do this thing, reshape -1, 1. Don't worry about it. It just makes it so that your X looks like a matrix to scikit-learn instead of like an array, right? Because an array is like 1 dimension, whereas a matrix is 2 dimensions. And scikit-learn only accepts matrices as input. It won't accept X to be just a single list. So the point is, don't worry about it. This reshape -1, 1 call, all it does is it just shapes it so that now it is a matrix instead of just the array, and scikit-learn will accept it as input, right? So X is just my column transformed in that way. Y, it will accept as just a list. So for the Y value, I just say it's equal to the life expectancy column of my data frame, and check it out. Before, we did all that formula stuff, but here it's even easier. We just do reg equals linear regression, right? So this sets up the model, kind of like our call before set up the model, but before we had to specify a formula, whereas in this case, it figures out the formula by just looking at the X matrix and the Y list, right? So it just like says, okay, the formula is whatever 2 variables you give me, right? And so linear regression.fit, and you give it the X value and you give it the Y value. And if you print out this reg object, it's not very useful. It just says like, it's a linear regression. So not that useful to display it on its own, but it has properties which help you do the homework, right? The project, where, okay, if you do reg.score, right, and you give it the X and Y, that computes the R squared, right? So that computes R squared, and we talked about how to interpret that before. So I'll run that now. Oh yeah, I have to run everything from the top. Okay, let's do that super quick. All right, no. What happened? Oh, I forgot to change my kernel. It's in the Python 3 default kernel. So let me change to DSUA-111 kernel. All right, and now I will run everything. It's the same as before. I'm running all the way up to the regression part. And blah, blah, blah. Okay. And I run the regression. Now, check it out. So if I print reg.score xy, it gives us our R squared value. It's the same one we had, right? 11%. So refer to that one for how to interpret it. It has this property coef underscore that gives us the coefficients. It's a little different from stats models in that this only gives you the coefficients on the independent variables, right? So we only had one independent variable, so it's just a list with one element, and that's our coefficient that we found, right? 0.0387. You can look, it was same as what we had in the other notebook. That's here. Yeah, 0.0387, cool. And so we print that. Now it has intercept underscore in case you do want to get the y-intercept, and that'll give you 67.8297, same as we had, 67.8297 for the intercept value. And it has this predict function, which is nice because sadly, unlike stats models, it doesn't automatically have a function to give you the residuals, right? So all you have to do is run reg.predict, right? Because that tells you like, oh, what does this regression line predict for that value of X? right? I have to do the annoying reshape thing here, but the point is like, I'm just giving it 50. So like, I'm saying, hey, scikit-learn, if I gave you a country with 50 years of independence, but you didn't know the life expectancy, what would the regression line predict for that country, right? And so here it's saying for a country with 50 years since independence, it predicts a life expectancy of 69.766. Cool. And so we can use that predict function to compute our residuals, right? Where we take the predictions, we just say predict, but just using all the x values, right? Using the actual data, meaning take the actual data, but only look at the x value, right? Only look at the years since independence, and tell me what you would predict as the y value, as the life expectancy value for each of those x values, right? And so, right, it predicts, here's the first 10 predictions, predicts the first country to have life expectancy 71.586, second country 71.818, third country 69.92, right? And so we can see real quick. So for the first country, it has like 97 years since independence, and it predicts 71 years life expectancy. Second country has 103 years of independence, predicts 72 as life expectancy. Third country and the fourth country have only 54 and 41 years of independence, and that's why it predicts lower values for the life expectancy, right? Because we expect that as you get more years since independence, your life expectancy goes up. But low values of years since independence, like 41, 35, will correspond to low predicted values of life expectancy. Cool. And now the residuals is just the difference, right? So you take the actual, here I'm taking the actual life expectancy column in my data set, and I'm subtracting what it predicted. Cool, and I get the residuals, and I make the residual plot same way. Okay. Yeah, let me run that and that. Same, it's the same exact plot, right? So I got my residuals here by just taking the actual column of what the actual life expectancies for each country were, subtracting the predictions that my regression model makes for each country. Cool. All right, and everything else is the same. So I'm gonna end there. Like, please note that this is like a super fast run through, and it's just because I wanted you to be able to have some code that you could look at and you know, mess with to be able to run some regressions for your project, because I was getting like super annoyed that we hadn't covered it in lecture yet. But anyway, that's neither here nor there. It's fine. Now you have two notebooks, right? One using stats models package and the other using scikit-learn package to do regression on just like pandas data frame. We have two variables that you want to find. You want to estimate the effect of one on the other. So yeah, like I said, if it seemed like I was zooming through stuff, it's because I was. And so really, like, this video is like marginally helpful, but what will be really helpful is like you going more slowly through the Python notebooks that I emailed you